we go. Hello. Welcome to week 16. Next to last week of the semester. Anyone out there live, thanks for being here. We don't have a super exciting day of content today. I actually think next week's content is more interesting, but got to finish the thought that we started, which is in a class like this, one of the things we're trying to do, and I think just traditionally it's considered to be a way to make a better computer scientist, and you could say also a better programmer specifically, is to have some sense of what is going on underneath those high-level languages that you use. So this semester we've looked at how is the data actually represented on the system. And we've also looked at the way high-level languages in the form of HLA interact with those underlying data storage techniques. And then we've looked at the way processors do arithmetic, manage memory, how do we access memory. And then last week we looked at what is a high-level language hiding from us when it comes to high-level decision-making constructs like if statements or switches. So this week we'll do what do loops look like under the hood. And then next week we'll look at what does floating point actually look like on the processor, which I find very, very interesting. More interesting than loops, because loops is just a different take on decision-making. It's just a way to control the flow of execution of a program. And all a loop really does, of course, is return the flow of execution back to some earlier place in the executable code so that it can be repeated. But I do think personally that teaching this, I've become a better programmer, and hopefully just kind of having the one semester where you get your hands kind of under the hood a little bit, it might help you in your programming work as well. Anyway, so I don't think it'll take super long because there's not much to any of that. We're not adding anything that you need to use for the second project. So this is just new content to experience. We'll have a lab homework and discussion as always, but nothing really surprising since everybody has seen how low-level decision-making works. Okay, so we are in week 16. So the second project is due this coming Sunday with all of the other assignments for the week. Really, you've had, since the end of week 13, so 3 weeks ago, you had all of the techniques that you needed to complete the project. Some of you have been working on it. Some people have actually submitted their project already. So please don't wait till the last second. It's not a huge program, but it is bringing together a lot of the bits and pieces that we've practiced with, and it's not trivial because the coding work at the low level is complicated. Okay, let me walk through the module and then do the few examples, and I expect that we will be done fairly early today compared to our normal routine. So same stuff. We're going to use labels to mark places that we can jump to. This time we're going to be able to jump backwards. That's how loops work, is they use jumps to go back or sometimes to go forward, depending. We will use the above, below jump semantics for unsigned comparisons. We will use the greater than, less than semantics for signed comparisons. All the same stuff. It's simply a matter of some of our jumps are going to go backwards because that's what loops do. So the readings. Druid asked a question, can you talk about efficiency in programming today? I can, yeah. So I'll address that question, Druid, after I get, that'll be the first thing that I talk about when I sort of step through these module pages and hopefully, and then we can kind of tease out if I don't answer it exactly what you meant then. But yeah, give me a moment and we'll talk about that first. Okay, so readings. Loops, again, it's the same techniques that you use for decision making, except for you're going to have jumps that go backward in time. Backward, higher up the sequence of instructions. Homework as always. The lab. So I'm going to show you the lab, and I don't have to come back to it, but the lab is the same program. It's literally the same program as last week, I think. Isn't it? Or did I make a small change? Negative, even, reverse the sign, see if it's prime. It's the same program. This time, all you have to do is the loops. And how many are there? There are 6 loops. So one less loop than there were decisions last week. You do not have to do the decisions. You will see in the lab assignment, it says, just implement the numbered things. And the numbered things are all saying translate a loop. So translate a loop. That means you can leave the decisions behind and just focus on the loops this time around. But it's the same program. And then some people have already started the discussion, I think, the little history of for loops, which is just kind of interesting that there is such a thing. And then this week, homework lab discussion, as always, plus the project, which is due on Sunday. So that's the week ahead. So there's a question in chat about efficiency in programming today. So one thing I would say is that those of us working in high-level languages, we don't have to work nearly as hard to make efficiently executing code as we used to, because the compilers, the compiler technologies have gotten so good that compilers can do a lot of the work for us of taking our high-level code that may not have been as efficient as it could have been and turning it into an efficient executable. So a lot of the trouble of making efficient software has actually been taken out of our hands because the compilers have gotten so good at doing that for us already. So just sort of keeping that in mind. The world of the modern software engineer, for most of us, is a lot easier than it used to be because we have optimizing compilers. We have every device that anyone ever programs for has got so much RAM in it that we rarely have to worry ourselves about staying within strict RAM limits. For most of us, that's true. Places where efficiency is still a premium are places like working on embedded devices. So for example, if you were a software engineer working in the automotive industry and you were writing software for the little sensor and control systems that are, in modern automobiles by the dozens and hundreds sometimes, then you are working in resource constrained environments. Those tiny little sensors and the control systems for them are very, very resource limited. They don't have a whole bunch of RAM. That the software needs to be very efficient. But even in those industries, there are language and library standards that kind of do a lot of the work for us, and tooling. So if you were working on a microcontroller that was going to be placed in a car, you would actually probably be aligning yourself with one of the automotive industry's coding standards, which are designed to prevent catastrophic failures in systems that do things like control automobiles. And they have all kinds of verification tools that they can subject their software to check themselves to see if they're staying within the resource limits and that they aren't violating any of the standards that are designed to make sure that there is error-free, bug-free, reliable software. So yeah, we've got it pretty cushy these days. Very few people, unless they thought it was interesting, would ever write in actual assembly anymore. It used to be that people might write a C program, say for a fighter jet control system, and in that C program, there would be sections of the code that they want to be highly optimized, and they would embed a small section of assembly code directly in their C program to make sure that that section of code was as optimal as it could be. but I don't know that anyone has that concern anymore. If you were to go work at SpaceX, I understand you're probably going to write the systems in C++, and use optimizing compilers, and that's how that would probably work. I say this because SpaceX was at a game conference that I was at a couple years ago, and they were recruiting people, and that was one of the things they were looking for with C++ programmers. So then it sort of comes then, should I bother myself, I suppose. Yeah, so then Druid asked as sort of a follow-up question. So it's kind of the people who are making the compiler technologies who are worrying about how to get the most efficiency. And the answer is yes, that's true. Now, I would still say that it's a best practice, even with an optimizing compiler and all of the tooling that can help us. I would still say it's best practice to use, for example, data types that match the needs of your software. So there's no need, for example, to have an array of integers if you just need a single integer. That's kind of an extreme example. But there's no need to have a 64-bit integer for a value that will never exceed 100, let's say, from 0 to 100. So I would still say it's best practice to be mindful of the data types you're using in your code. It's still best practice to be mindful of introducing code into a system that kind of does unnecessary work or does unnecessary repetition. Yeah, a lot of compilers will catch this kind of thing as well. So I'm trying to think of a good example of that that I see sometimes in my teaching work. Well, it's a bad example, and I haven't really seen it very often, but using a loop in your code. So this is kind of, it's related, but not the same thing as efficiency. But if you can imagine a person who puts a loop in their code that performs a single action sometimes, but not other times, and only performs it once, that would have been better expressed as a decision, of course, because putting a loop in your code suggests that something may happen repetitively. So I would argue that that's maybe not efficiency that you're looking for in terms of how fast the executable is, or how kind of minimizing the amount of space that it consumes in RAM. But still, there's kind of an efficiency in terms of you and other people working with software and having the code that you write reflect accurately the ideas that your algorithms, that are your algorithms, if that makes some kind of sense. One last thing I would say about, just for now, about efficiency is there's a lot of debate among the new language creators. So the Go language, as an example, which I think is a very elegant language, but the designers of that language have made decisions about the way that technology works that end up with very, very large executables. So in the Go language, when you compile an actual application in the Go language, they are very, very large because they incorporate a lot of the standard libraries that may or may not actually be used in that application, at least as I understand it. So they're trading some simplicity for, in that case, maybe I wouldn't say it's inefficient, but they're allowing for larger executables to be produced at the sort of compiler end of things, so that they can reduce the complexity at the programming end of things. Whereas a language like Rust, sort of at the extreme, in my opinion, C++, those languages kind of introduce more of the complexity into the life of the programmer. But in doing that, their compilers can actually produce smaller executables. And that's literally just like the file size of the executable coming out of a C++ coded program is much smaller typically than the size of an executable file that comes out of a Go program when you've written it. And some of that is just based on either putting more complexity on the libraries that are in the compiler or more complexity, kind of a mix on the shoulders of the programmer. So yeah, so Druid in chat says they would have thought that it might be the opposite about the Go language versus C++. But yeah, if you think about it, Go is trying to reduce complexity for the programmer, which means that somewhere in there the work has to be done. There's also debates, by the way. You can go look at benchmarks for this. They're called benchmarks. People compare the speeds that compilers can actually take code and produce executables off of. I don't know off the top of my head a comparison, but you can look at a comparison between how fast does Go source code become executable versus C++ become an executable versus Rust become an executable. So that's a compiler issue as well, but that's kind of where you see, I think, a lot of the attention paid to efficiency. There's more attention, as my closing sort of comment about this from this question. Thank you for asking. It's cool to talk about, I think. There is more attention. What was I going to say with that? There seems to be a lot more attention being paid sometimes to safety. And what I mean by safety is largely data types. And if you think about a program and where data types come into play, it's all over the place. Introducing variables, assigning values to variables, writing functions that return values. So there's a lot of attention being paid in programming language and compiler design these days, it seems to me anyway, on safety. Trying to make programs that basically they won't compile if they are incorrect. So they're trying to sort of make the compiler be a lot more strict and check a lot more thoroughly the programmer's use of data types throughout their code to catch mistakes or possible problems at the compiler level, as opposed to waiting for a runtime to expose a problem like that. So yeah, I'm very interested in myself in programming language design, which of course carries with it the need to build compilers. And there's a lot of languages out there being kicked around right now. So Rust is kind of an up-and-comer. Elixir is, to me anyway, an up-and-comer, but there's a language called Zig that seems to be getting some attention. Gleam is a language that I think is kind of cool. So there's a lot. It's a fun space to go play around with if you're interested in such things, to see how people have different ideas about how to express our algorithms in code, and then kind of look at what happens down the tool chain, as it were. So what does the compiler do with that? How do libraries work with it? The resultant executables, all that stuff. So anyway, thanks for that question. Hopefully that's close enough to kind of getting around the question that you asked. Yeah, so for our purposes, we are usually pretty spoiled, and we can spend more time focusing on the correctness of our code and our algorithms then we need to worry about the efficiency of our code and algorithms, which is a great thing to have. It's a luxury to have that. Okay, let me switch views and we'll do the few loops that we have and perhaps call it a day. Okay, so good. Hopefully, Druid, that was kind of in the ballpark of what you're interested in talking about. I forgot the password for, oh yeah, student. All right, so not much super exciting to do because the labels and the jumps are all the same, but let's go ahead and put the loops that HLA allows us to use and then translate those into low-level code. just for the practice. And I'll share these this code as notes. Yeah. Okay. So this is actually for the most of you probably have had the Go language at Butte College. If you haven't, then this won't make as much sense. But one of the interesting things why we have it in front of us, one interesting language design decision that they made in the Go language is to get rid of all the different kinds of loops and just use a one loop construct. As opposed to C++ now, which has the while loop, the do while loop, the for loop. They have the for loop that uses the built-in iterators, kind of a for each loop. C++, as far as I can tell, the designers and maintainers of C++ never saw a programming language idea that they didn't like. So it's like the buffet at the Rio. If you've ever been to Las Vegas, everything's in there, which some people like, some people don't. But the Go language, interestingly, just has the one loop that it uses to pull off all the other kind of loops, which obviously is doable because the Go language is perfectly usable for all kinds of, it's a general purpose programming language. So for us, the while loop is the same as the C++ while loop. In HLA, the repeat until is like the do while loop. So the difference between a while loop and repeat until is when the loop breaking condition is checked. So for a while loop, the loop breaking condition happens at the beginning of the loop. The repeat until, the loop breaking condition is checked at the end of the loop. The for loop, what's interesting about it is that it, at least in a high level language, has embedded within its syntax the counter initialization, the counter adjustment, the increment, and also then the loop breaking check, which happens at the top of the loop. So the for loop is really just a while loop with the loop control variable kind of baked into its syntax. And then the forever loop, which not every language has, but every language, well, Go has one. The forever loop is really just a loop where the loop breaking condition is checked at some arbitrary place inside the loop's body based on the needs of the programmer. It's a convenience as much as anything. So really you could do all of those loops with just a while loop or just a forever loop, which is kind of what the Go language decided to do. All right, so let's write one. We'll just say move al while al less than 5. Let's keep the number small. So you can already kind of see here, by the way, that we got the makings of a for loop, where we have the sort of the counter, and then we have at the top of the loop, before any of its contents execute, is the logic. Then we have the contents themselves, which I'm just going to say, ooh, let's be cute and put the hex out just for fun. And a space after, and then I'll put a new line at the end. And then we're going to need to increment AL. All right, so simple loop, right? There's no big tricks here except for us computer science people and software engineer types, programmers. It's just to kind of remind oneself about the design of the while loop, which is that the condition is checked at the top of the loop. The implication of that, what can happen because you check the condition before the loop body executes, is that a while loop can execute 0 times. Let me run that just to All right, so as expected, I printed them out in hex because I thought it'd be fun to do that. So there they are in hex. All right, so now let us do that same loop. Let's see, I probably, new line. Yeah, let's put an extra new line in here. And then I will put some, well, what symbol do I want? I probably just dashes. Just to break up before we start the next section. All right, so now let's do it in the low level style. So I'm going to move 0 to AL, noting that the initializing the counter happens the once and only once, so it's not actually a part of the looping construct at all. Start while. So now we start the while loop. It's a while loop, so we do the comparison of AL to 5 at the top of the loop. And then we say if we are above or equal to 5, we're doing unsigned here. So if AL is above or equal to 5, we will jump to the end of the while loop. So put that label in there. And then in between those, so if we don't do the jump to the end of the while loop, then the loop body will execute. So that's what makes a while loop, is that the condition is checked at the top. So take these things, do the loop body just like we did in the original one. And then the last thing, this is the thing that makes the thing a loop, is what happens after we do the increment. Well, in an end while, we kind of just learn to read that as well. It's going to jump back and reset to the top of the loop. In assembly, of course, once we get to the bottom of the loop, we unconditionally jump back to the start of the loop. And then I will put a new line after the end of the loop. Except for it didn't tab over. All right, so it's a little bit less. Sometimes I think the decision making at the assembly level looks like about the same amount of work as a decision. But doing a loop in assembly is actually typically more work, more instructions than a decision, because you kind of have the extra jump to go back. It can depend, but anyway, there's that same loop. I don't think that there is a much more efficient way to write it in assembly. Maybe there is, but it should produce the same result. So that's just confirmation that it did. Now I don't like the extra new line. All right, there we go. So that just the high level while loop, the low level while loop, producing the same result, which is a confirmation that it's probably correct. So no big surprises there. The above, below semantics, because I'm doing unsigned comparisons. The unconditional jump to get us back to the top of the loop. And then eventually we're going to jump over the body of the loop when we get to AL being greater than or equal to 5, then we're done. We jump over the body and continue execution below the loop. So, well, look, I'm actually going to do this. I think I'm going to, no, okay. So I'm going to do it this way. Cut that out, put that down here, and then comment it out. All right, so there's a while loop. We can do a repeat until loop. So we will move 5 to AL, and then we will repeat. This time I'm going to typecast AL just to make them look a little bit different. And then maybe I will put a dash after each one. All right, so there's a repeat until loop. the main difference here, and it's one of the things to remind yourself about the way these looping constructs offer you these different options. So a repeat until is guaranteed to execute once because the controlling logic is not checked until the body of the loop has already executed. So in this case, in fact, we can make it 4 and increment it. In this case, it's going to execute once and then immediately break. But even if I made this 5, oh no, that's bad. Let's say greater than or equal to 5. That would have been an infinite loop. Okay, so anyway, that's the thing to remind yourself. The do while loop in many languages, the repeat until in HLA, the Go language does not have this construct. It just uses variations of for loops. But anyway, this one, the loop body is guaranteed to execute once. So let's just check it. It's going to execute once with the dash behind it. So that's as expected. Yeah, so Druid asks, is this code... So it's not infinite. I just executed it. But no, so Druid, I made this change right here, which prevented that problem. So I did have AL equal to 5, and that was going to be infinite. Well, not entirely infinite. It will wrap around. Once it wraps back around at 255 to 0 and then to 5. But Druid's right. I had originally written this as double equals, the equivalents. But if I start AL at 5 and then increment it, AL would be 6, and those would not be equivalent, which means that effectively that would have been an infinite loop. It would have wrapped all the way around unsigned 8-bit. Would have gotten to 255 and 0, 1, 2, 3, 4, 5. It would have taken it all that time to get back around. So you were right. I did initially do it with kind of an infinite loop setup, which was a bad idea. Okay, so the thing again about repeat until, the logic is checked at the end, which means that repeat until loops may execute, will execute once, guaranteed, and may execute more times. All right, so let's do this thing. In the low level style. So start repeat, and then just take this stuff. So we do the loop body first to get this kind of a loop. And then we will compare AL with 5. And then we will say jump below, start repeat. So one thing that's awesome about this, by the way, so look how much less instructions have to be spit out for a repeat until loop. It's super efficient in terms of the instructions that have to be emitted to represent it, because you only need the one label that you go back to until you don't go back to it anymore. So that, I think, to me is sometimes instructive, just to think about, even for an optimizing compiler, what kind of work is the computer going to have to do for different kinds of loops. I don't usually I don't change the kinds of loops that I use based on knowing how this works. Because I think in high-level programming, what you want to do is you want to select constructs that express your ideas in a way that not only the computer can execute it, but also that other programmers looking at your code can understand your intent. So the reason why we would use a repeat until is because we know we're going to execute the body of the loop one time at a minimum. The reason why we would use a while loop instead is because we don't know for sure always if we're going to execute that loop body 0 or more times. So anyway, just things to think about. There's no kind of right or wrong as long as the loop actually works, but yeah, I would argue that you should try to select constructs in your programming language that most clearly communicate to people looking at your code what your algorithm is meant to do. You could say that takes practice, but if you go back and this is an exercise in humility, but I've done it. Go back and if you've kept any of your old software that you made, go back and look at some of the early stuff that you did, and like it's not, you will find, like I did, that you were terrible and you made all kinds of terrible decisions that don't actually clearly express the algorithms. It's just a big gnarly bowl of spaghetti mess that happens to work perhaps, but is not the clearest expression of an algorithm. Anyway, give it a shot if you have. It is humbling to do that. New line. All right, so there's that same loop executing the once and then breaking the condition. Of course, I can adjust that if I want to. Even if I make those 4, by the way, the incrementer is still going to get it to 5. But there is one small difference. They're both 4s because the increment happened second in the body, so it didn't grow to 5 until after the output happened, and then the 5 broke the loop. All right, so there's repeat until. I'll label these. Repeat until loop. How can I make that more? That's fine. Maybe I'll put some stars next to it. All right, so there's the repeat until loop. Doing good on time. Let's do a for loop. What happened? I deleted. Oh, I accidentally grabbed the end of the program. All right, so a for loop. So again, sort of in the Go language, it's different because the for loop is the only looping construct. So you use the for loop with different configurations to get different looping behaviors. So the Go language has a forever loop, which is just 4 with no condition. It has a traditional kind of counting for loop, which is what I'm going to do simply by configuring it to have the counter and the logic and the increment in it. It can do the for each style loop by ranging over things. Anyway, so the Go language is kind of interesting. I'm going to do the traditional C++ counting for loop. Yeah, this will be fine. So all of the sort of loop controls are sort of baked into the syntax of a HLA for loop, just like they are in C++ and can be in the Go language. So I'm using CL as the counter. So the thing to note, though, is that you all know this kind of intuitively at this point, but that setting up the counter actually happens before the loop begins to execute and only happens the once. And then the logic is checked just like a while loop, and then the increment is done at the end of the loop. So a for loop is really just a more convenient form of a while loop in many ways. or more complicated based on your own preferences, but I would call it a slightly more compact while loop, basically. So before the loop, top of the loop, end of the loop. That's how it works. So we will just do the, we'll typecast again, unzate. AL. Let me put a comma between them. Ooh, let's do a whole thing. Yeah, I gotta do it. So if CL less than 9, then yeah, that'll be it. So let's just make sure that that works like I wanted it to before we move on. What? Oh, AL. What a dummy. Just print out the counter. Let's start at 1. Let's go to CL all the way up to less than or equal to 10. CL is less than 10. Should get me 1 through 10 with commas in between, except for not at the end, right? Yeah, that's what I wanted. I also wanted to make myself work a little bit harder to translate this thing into assembly. Okay, so how would this look translated? Well, it's more or less a while loop with a lot of the syntax baked in, sort of compressed, if you will, or yeah, that's how I would say it, is the for loop kind of just compacts all of the while loop syntax into this one statement. So we would do this. Now we have the for loop starting. We check. And then we jump above. So we stop when CL goes above, but as long as it's below or equal to, we're good. All right, so that gets us out. Then for starters, we'll just put the if statement in intact. There's no need to translate that immediately. And then before it's all said and done, we have to unconditionally jump to get the, oh, I forgot a thing. Forgot to increment the counter. Now we can unconditionally jump back to the beginning. All right, so there is the for loop, which is pretty much the same thing as the while loop. Start the counter, but outside the loop. We check the condition at the top of the loop, just like a for loop, a while loop. But that's what for loops do too. We do the body of the loop, and then at the bottom of the body, we increment the counter before we jump back to the start and reset and run the comparison again. So I'm going to leave this if statement, and then I'm going to translate it here in a moment after I make sure that this produces the same result, which I need a new line there at the bottom. Oops, I forgot to, I put a semicolon on the end of the N4 label and not a colon. So don't forget, when you define the label, it's a colon. When you jump to the label, it's a semicolon because it's an instruction. All right, better? All right, so same result. Now let's, just for fun, go ahead and do this if statement in the middle here and see what that would look like. So I'm going to comment you out. So I have another comparison. Compare CL and 10. If it's less than 10, below 10, then I do something. So I'm just going to say jump above or equal to an end if And if I don't do that jump, then I will do the standard out dot put. All right, so there's a little if statement right in the middle of it, but I wrote it backwards. I used this kind of opposite of the high level logic because that makes the low level easier to write. So instead of checking to see if CL is less than 10 or below 10, and then doing something, I actually see if it's above or equal to 10, knowing that I don't do the thing, which is really what the if statement does. Is it jumps on the other condition. If you think about it, it doesn't jump when CL is less than 10. It does jump over the body of the if statement when CL is above or equal to 10. So I captured that like this. Some people might kind of just shove the thing over so you can still keep track of who the while loop, where the while loop begins and ends. Up to you. Should still produce the same result. Okay, so all is good. Let's get that out of here. One more loop. All right, last loop is the forever loop. Just because I felt like it. So we're just going to forever print out lions and tigers and bears, oh my. And then we will do a standard out dot put. Go again. Yes, no. Probably don't need this, but yeah, it's fine. I'll go ahead and do it. Oh wait, I'll just do a break if. Let's see if that works. So there's a forever loop. It's using a break if, which is a really cool HLA construct. Of course, in a high level language like C++, you'd have an if statement with a break inside of it. Because in most high level languages, break statements are used to break the nearest loop, not the nearest decision, right? So you can put a break inside of an if statement inside of a loop, and that break inside of an if statement inside of a loop breaks the loop, not the if statement. But let's make sure that this works. Because I don't... Did I mean to upper? I don't know. Did I? Is that a capital U? I don't know. Is that what it is? I guess so. Go again? Yes. Yes, 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 yes. No. All right, so let's translate that. Forever loop. Bring these guys over. All right, so now as a low level. Let's see if I even need both of these. I may not. I think I can get away with not, but let's try it. Where did I put it? There it is. Okay, so now we have to do a comparison. So I'm going to compare chars dot to upper AL with no. Yeah, I don't need the end. It's like a repeat until kind of, because only I can say jump not equal to the start. And that's the whole loop, isn't it? I believe it is. So I believe that's going to work, and I didn't need the extra label. All I need to worry about really is, now of course the real trick to this is that I had the break if. So I'll update this in a moment, but since I had the break if at the bottom, this is more or less a repeat until loop, which means it was very easy to translate with not very many instructions. No. All right, so now we'll try it again. Yes, 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 yes. No. All right, so that all worked. Let's try it. Let's add a little thing to it. So let's see what happens if we were to do, no. Well, yeah, okay. No, so Druid asks in chat, is it bad form to have an end forever loop here, even if it is inert, as it were, even if it's not actually used? And I don't think it's bad form at all, personally. It has no effect in any way on the executable as far as I know. So I think there is no harm in it at all, having that loop just to mark what is meant to be the beginning and end of the loop. I don't think there's any harm in that at all. So I would totally do it in my code if I believed it made it more readable. And you could argue that that's a good idea because now I know that the new line is not part of that loop. It's actually outside of it. I mean, I guess you could do, the other technique you could do is a comment, which would be more or less similar, right? An inert thing that has no effect. Yeah, you could do it either way. So let's see what happens if they say yes, go again. I'm going to print a thing, and let's see if that changes my loop at all. So if I put something after the break if, I need to think of something kind of like lions and tigers and bears. Oh my. So let's see what implication this has for my other loop. If they say no, well, let's just run it so you can see what I mean. So if they say no here, then we jump straight to the other loop. But if they had said yes here, it says there's no place like home before repeating lions and tigers and bears, oh my. So let's see how that works for my low level loop if I need to get this bit into this other loop. So if I need to get that bit into the other loop, yeah, it's going to change the logic a little bit. Jump, start, forever. So look at the implication here of having something after the break if statement is it turns it into a different kind of loop. So let's see, jump equal, in this case I need the end. I need to be able to jump to the end. So the act of putting that extra bit of code after the break if, something additional in that loop, should they say yes, cause me to have to jump over it on a no and then jump back to the beginning on a yes. So the placement of that break if makes a huge difference. It makes all the difference. All right, so it will say yes, it'll print there's no place, and then I'll say no, and then I'll say yes, it should print there's no place like home, and then no, it should jump out of it. So anyway, there you go. There's the forever loop, two different setups for it. I'll just leave it like that. What else do I have? Yeah, so I already talked about the lab. Is the same program as last week with the same functionality. So the puzzle to solve is to replace the loops only and still have the same functionality intact in the program. Um, Project 4, there's nothing else for me to add there. We talked about it last week. It's fairly basic. It does require that you do the the dynamic arrays, and then the work to access memory using indexed and or scaled indexed addressing on that dynamic array. But those are things that we got through during week 13 if you're looking back. Okay, I think that is all I've got for today. Next week, hopefully you'll find what I do next week cool as well. I mean, it's just very interesting and crazy complicated, to me anyway, how floating point numbers actually work. The big insight next week, by the way, is why do floating point numbers, why are they such a huge hassle in programming? Why does it seem like they are frequently losing information? And it's because of the limitations of doing floating point on a modern processor. So anyway, hopefully you'll get those insights from next week's work. So this week, lab, homework, discussion, and the second and last project due on Sunday. Next week will be a normal week with the last bit of content with a lab, homework, and discussion, and then the semester will be over. So I'm glad you are going to make it all the way to the end with me. I appreciate you being here if you could be here live. Thank you for the questions in chat. Those are always helpful, and I'm sure lots of other people would like to have those same kinds of questions answered as well. So have a great week, and I will see you on Tuesday afternoon next week.